First of all, welcome to webinar 3 focused on manufacturing analytics of the webinar series Data Science, Machine Learning and AI Applications and Opportunity. We all know that data science, machine learning and AI has recently become a power engine transforming various manufacturing applications. And in this era of smart manufacturing and Industry 4.0, the abundance of smart sensors and industrial Internet of Things have made manufacturing systems a data-rich environment. Data science and machine learning plays a significant role in uncovering fine-grained complex product patterns and offering timely decision support and actionable intelligence in a wide range of applications. To name a few: robotics and human-machine interaction, predictive maintenance, process optimization, task scheduling, and quality improvement and inspection. This webinar is continuations of the discussions in manufacturing analytics domain that we started last week, and it is dedicated to harvesting the latest research and development in machine learning in manufacturing domain. And I have invited a distinguished panel of three eminent researchers who will be talking about the research in this domain. Before I briefly introduce our panelists, what I want to quickly do is I want to take 1 minute of your time to make an announcement for the next webinar series. So today we are talking about manufacturing analytics, but if you're interested in the next webinar series, which is webinar 4, which is focused mainly on industrial applications of data science, machine learning, and AI. And we have speakers, Dr. Prakhar Jaiswal from Google, Dr. Ian Matei from Palo Alto Research Center, and Dr. Jawad Sobizi, who is the lead data scientist at Baker Hughes. So I will encourage you to join that seminar too. So with that, let me come and I will basically introduce today's panelists. And we have 3 eminent speakers. First of all, we have Laine Mears. Laine is BMW Smart State Endowed Chair of Automotive Manufacturing and is also University Centennial Professor and founding faculty member in Automotive Engineering Department at Clemson University. He teaches and conducts research in manufacturing process control, new process development, and manufacturing equipment diagnostics. He has published over 200 peer-reviewed articles and is the recipient of NSF Career Award, SC Ralph Teeter Educational Award, and South Carolina Governor's Young Researcher Award for excellence in scientific research, and the George Stephenson Gold Medal and Thatcher's Bronze. In addition to academic experience, Dr. Mears has over 10 years of experience in industry, having held positions with Hitachi Automotive and SKF Bearings, both as manufacturing engineer and engineering manager in high volume precision manufacturing environments. Dr. Mears has a BS in mechanical engineering from Virginia Tech in 1993, and MS and PhD 2001 and 2006 in mechanical engineering from Georgia Tech. He is fellow of both the American Society of Mechanical Engineering and SME, and is a senior member of the American Society for Quality. Our next panelist is Thomas Hedberg. He directs the acquisition and industrial security mission at the Applied Research Lab for Intelligence and Security, which is termed as ARLIS, a DoD-sponsored UR at the University of Maryland. Dr. Hedberg joins ARLIS from the National Institute of Standards and Technology in NIST, where he was the program manager of the Model-Based Enterprise Program and the co-leader of the Smart Manufacturing Systems Test Bed, which earned him the US Department of Commerce Gold Medal. Dr. Hedberg is the chair of ASME MBE Standards Committee and a member of the several ASME Y14 committees and a past member of ISO TC 184, 12, 15, 21, and other committees. Dr. Hedberg earned his BS in Aeronautical and Astronautical Engineering from Purdue University, and M Engineering in Engineering Management from Penn State University, and PhD in Industrials and Systems Engineering from Virginia Tech. Our third panelist is Zhenyu Kong, who is currently a professor with the Graduate Department of Industrials and Systems Engineering at Virginia Tech. He received his PhD from the Department of Industrial and Systems Engineering at the University of Wisconsin-Madison in 2004, and BS and MS in Mechanical Engineering from the Harbin Institute of Technology, China in 1993 and 1995. His research focuses on sensing and analytics for smart manufacturing, modeling, synthesis, and diagnosis for large and complex manufacturing systems. His external research funding amounts to over $15 million, with a personal share of $5 million sponsored by several US federal agencies such as NSF, DOE, DOD, ONR, and DODT, as well as industries. He has published more than 60 peer-reviewed journal papers, and his research contributions has been recognized by 8 Best Paper Awards and Posters Awards in various conferences. He has been honored with a number of awards, including the 20 most influential academies in smart manufacturing, honored by SMS Smart Manufacturing magazine in 2021. And he is also a fellow of IISC in 2019. With that, I will welcome all the panelists, and we will get started with the presentations first. Our first presentation will be carried out by Dr. Laine Mears.
Excellent. Thank you, Dr. Rai. And in the future, no need to mention my BS graduation year because I'm older than I look. Let me see if I can share. Okay. I want to make sure I turn the sound on. Here we go. Great. So I'm trying to hit, whoops. Oh, never mind. I'm trying to hit under 10 minutes. Can you see that screen? Okay.
Yes.
Large. Okay, perfect. Try and hit under 10 minutes. So I'll go through some things pretty rapidly, but there are a couple stops I want to make along the way that are pretty close. First, as you know, after I chastised Dr. Rai for mentioning the year here, I put it on my slides too. Anyway, this is sort of meant to show. You know, I've got an academic side and I've got an industry side. And I think that's a really powerful thing, at least for a professor, is being able to say, I've been out there, I've been in the trenches, I've gone and made ball bearings, as exciting as that sounds, but I learned a lot, you know, while I was doing it. And then this has led me to, when I stepped in, that's a younger version of Laine in the lower left, on our new campus for automotive engineering that was just getting launched. And we've really built that up into a program. I'm very proud to say we're sort of a worldwide leader in industry-focused education. This is a graduate program in automotive engineering, and puts out engineers and technical leaders that are finding all kinds of very interesting jobs. I, in this organization, as the Smart State chair of automotive manufacturing, run the Smart State Manufacturing Lab. And so in this way, we look at how some very interesting things that are happening in the automotive industry, very exciting things, are kind of driving us to rethink what the vehicle production system looks like. We've been making cars out of steel for 100 years. And they've had IC engines in them and transmissions, and all those things are sort of going away more rapidly than we expected them to. So a number of companies are really scrambling to figure out, okay, now I've got these multi-material structures that I didn't have before. I've got these new powertrains that I didn't have before. How are we going to put these things together, and how are we going to manufacture these things, and where are the materials going to come from? And all of the headaches that you have in a manufacturing environment multiplied because of the complexity. So we're looking at how the manufacturing process needs to evolve, and also how the people and their understanding need to evolve, both on the company side and on the students that we're training. This is a broad brush stroke of sort of the lab's activities. We look at sensor fusion, predictive modeling. We look at it in sort of a couple interesting directions. How do we bring all the sensing information together, and how do we use predictive analytics, machine learning, and some of the artificial intelligence tools to allow the process to understand more about itself? We've applied this in machining, joining, forming operations, and assembly operations. And when we get to assembly, we start to rub up against this weird element called the human being. and assembly operations are not going to be automated 100% anytime soon, at least on the vehicle assembly factory floor. So we look very closely at this Internet of Things and how people can get plugged into the Internet of Things. How can people become a data source, and how do people receive data effectively in order to be a good part of this new networked smart system? And so that drives us to think about how we educate people in that area. So I direct an NSF sponsored program in humans and technology interacting with one another. And the interesting thing about this is that we put graduate students, undergraduate students, and technical college students all together on teams to solve some of these complex human machine problems. And I'll tell you a little bit about that. I'd like to cast this brief talk in terms of looking at the industry 1.0, 2.0, 3.0, 4.0. We've heard that before. This graphic really tells a lot to me because it looks before those things happened, and it kind of looks to what's forming out of the ether of what's going to be happening. So I'll do just 3 quick examples, one to illustrate industry 4.0, one to illustrate biological manufacturing, industry 5.0, the things that that people are calling how the humans and technology are integrating. And finally, one that's looking at real artificial intelligence and how humans and artificial intelligence are going to need to mix in the future. This is a really interesting area that we're working on a new NSF project in. So for the first, we look at predictive maintenance, and here we see bearings. So we picked bearings because it's relatively well understood how bearings fail, and so we have sort of some common sense to check us. This is an actual bearing failing in an actual factory, in an actual company that we are working with in order to better understand this phenomenon. So the idea is we have great predictive maintenance systems and a lot of people working in that area. And these systems are typically trained by putting a bunch of sensors on industrial equipment and then waiting for it to break, right? Waiting for it to fail. And when it does, a lot of times it fails like this. And so when you do the postmortem and you really take this thing apart and look at it, you don't know what happened, right? You don't know what the root cause is. So that drove us to sort of think about, okay, how would one know the root cause of such a failure? And how could we create data sets more rapidly than waiting for industrial equipment to fail, which sometimes takes months, years, or it never even happens. And all you get is a lot of baseline data and a really well-trained baseline model. So this is version 1.0 of a piece of equipment that we put together where we're failing bearings on purpose with known ways of imparting defects so we can create a more rich labeled data set. So we'd be able to see this is what it looks like when a bearing's running well. And this is what it looks like when a bearing's contaminated. And this is what it looks like when a bearing has a ball defect. And this is what it looks like when a bearing has a race defect, along the whole progression of that. So we're able to see this thing failing over time. And we look at it through a number of different sensors, not just the classical vibration, sound sensing, temperature sensing, visual sensing even. And then we do classification. So it's known classification. So we use these data sets to train predictive models, and then we turn around on independent data and test those things out. And the idea is, well, geez, why don't we do this to a very large degree and create very large labeled data sets, not just for bearings, but for all types of industrial equipment. That's some of the avenues we're looking at now. The second, as we step into the industry 5.0 realm, is looking at how do machines and people get along well together, particularly as we're peeling the onion back about these network data systems and smart manufacturing systems. And a lot of times we see people sort of getting pushed off to the side. Well, how do we bring those people into the fold? How do we make them part of this data system? And how do we make them enjoy it? There's some very interesting psychological factors that help us understand that as well. The figure you see here is on the left side, the upward facing pyramid is from a paper by Jay Lee that's very highly cited out of Manufacturing Letters, SME journal. And it talks to how cyber physical systems are really good at connecting, they're really good at converting data and transmitting data in a rapid type of fashion. And then as you get up higher, they're really bad at thinking and reconfiguring themselves and adapting. And his intent was, we need to develop systems that do that better. And we looked at that and said, we have systems that do that better. The great system is called a person. A person is rapidly adaptable and reconfigurable. They think really well, but when they get down to the multidimensional data visualization and conversion, they don't do such a good job. So we saw this as a really complementary kind of dyad. So when we put cyber physical systems together with people, they can complement one another. So we use that as sort of a driving activity and say, okay, how do we plug people in to this Internet of Things? We look at initial step as wearables. So we look at wearable feedback systems for people giving data to the system, and wearable systems for the system giving information back to the people. And so now we're closing the loop through the human, and all kinds of interesting things happen when we try and do that. So as a few examples that we've got here are some gloves that have sound, motion, temperature, vision built into them. And so now we can really see what somebody is doing. We like to think about this as information where there was no information before. Typically, we don't have this kind of data for manual types of assembly processes, and we're creating some very interesting data sets that we're ready to share with the world. And let me close with a final data science problem, but it's really more of an education problem, education as a data science problem. And here we stepped back again and looked and said, graduate students are educated here, undergraduates are educated here, and technical college students, drive about 20 miles that way and you'll find out where they're educated. But then they all jump into the factory together and they get put on teams where they're supposed to work together and use data to solve problems. How do they even know how to do that? So we created a education program where we put these different students in teams and they solve these human data problems in the manufacturing environment. In order to do that, we had to build the environment first. So we initially tried to do this in an operating vehicle assembly factory, and they weren't too keen on having a bunch of people running in and causing problems in a vehicle assembly factory. So we built our own, and we call this the Vehicle Assembly Center. So this allows us to come in, break things on purpose, make bad conditions, put people in weird situations, and allow us to sort of do what we do with design of experiments, where you really pull the lever really hard from side to side and see what the effects are. And it's worked fairly well. We're in our third year, and I'll close right here. And this is a picture of our latest cohort that's come out. They're working together in teams, they're working together in sub-teams, they're learning from one another. And these elements flow through the programs. You have to understand how teams work together. Everybody has to understand how to leverage data, and everybody has to understand sort of what your role is in the organization. This is Greenville Tech students working together with Clemson students. And it was very effective this time around. And so we're really pushing that, and we're starting some new mentoring activities in this area as well, so we can formalize the learning a little bit better. Okay, so I'll go ahead and stop there. Maybe I ran a couple minutes over. I apologize for that, but we're looking forward to the discussion.
Thank you very much, Laine.
Okay.
So now we will move on to our next panelist, Thomas.
Thank you. And let me see, I'm looking for, let's see, whoops, lost my panel there for a second. All right. So hopefully you can see the appropriate screen, full slide there. So I'm going to talk about really the application opportunities of this concept, digital thread, digital twin in manufacturing, which, to be quite frank, we see digital twin thrown around everywhere in that. And I'm hoping to clear up, at least from my own opinions, what this concept of digital thread and digital twin are, and what the opportunities for that are. Like Dr. Mears, I'm not putting a snapshot up here to toot my own horn, but really to kind of also say the same thing of, I came from the private sector. I was in industry for almost a decade before I went to the federal government. And now I'm in academia, which is, so I've kind of got a trifecta of experiences that I'm going to speak from in that to really provide some opinions. And I want to make sure, because I do work for a UARC and we are somewhat of a trusted agent to the federal government to maintain science and technology expertise, what I'm going to talk about today is really from my own perspective, my own opinions, and from my own experiences in that. And it's not to be considered a position of really my employer or the Department of Defense or the federal government. So the whole crux of what I'm going to talk about today is around data science, AI, ML, is this concept of what I call the connection interoperability paradox. And so we're going to use our classic XKCD comics to help us explain this, in the sense that, all we really want are secure systems where it's easy to do anything. Is that too much to ask? And what that really ends up being is that we have all these disconnected systems that we then try to mash together with hammers and screwdrivers and get all this data flowing. And then all of a sudden we realize there's a bunch of holes in those, and the security opens up. So it's like, hey, let's go back to secure sandboxes. And we just perpetuate this problem over and over and over, where we are trying to connect things. We realize things are too connected, that causes security problems. And then we disconnect them, lather, rinse, and repeat. So putting this into the manufacturing sort of context and really into a broader supply chain context in a moment, is that if we take the ISA 95 sort of view of manufacturing, that is where all the way at the very top you have your enterprise resource planning, your tools and capabilities, your business planning, logistics, and you work all the way down to the very bottom where your bits and atoms, your people and machines are actually doing things or doing work. The challenge that we see in manufacturing is that scaling information and what information scales either from the top down or from the bottom up is not well understood. And we don't have consensus on what those interfaces are to go across those levels. ISA 95 does a really great job of explaining each level. But what I've been kind of talking about for the last few years is that the lines that we draw to create those levels become artificial barriers. Tools and technologies were developed in each of those levels without thinking about how eventually those levels would integrate or how they could interface with one another. And that's quite frankly because when a lot of those tools were built or those technologies were developed, no one was thinking that an ERP system would gather or ingest all of this data coming from a process, from a machine tool. And no one thought about, okay, what are those interfaces and how do I do those abstractions and decompositions of that information as I go vertically? Same thing with across the life cycle. If I look at design through manufacturing into sustainment, we tend to say, oh, we just throw things over the wall, right? We've got these different cylinders of excellence, aka silos, that exist in design, manufacturing, sustainment. And when we were in paper-based processes, it was really easy for design to send a drawing to manufacturing, for that human to take that and interpret it and put it into the sort of formats and information that it needs to do. And then for that human to walk it across these levels all the way down to the people and machines in manufacturing. So we have this horizontal and vertical integration problem. And a lot of it boils down to is that when you look at what happens in each of those silos, either again, horizontally or vertically, you realize that everybody's saying the same thing, but in a different language. They all have a message that they're communicating, but it's being communicated in a different language. And this is true whether you're making gym shoes, dental implants, airplanes, ships, or cars. This is a problem that scales across all of these different domains and industries. And really what it boils down to is doing trusted decision making in distributed environments, using information, using data science is really difficult because of this messaging and integration problem. And you don't have to listen to just me. If you go look at the national security strategies that have come out over the last few years from different administrations, they'll say that having healthy and secure supply chains with skilled workforces is important to manufacturing readiness. Our engineering strategy of digital engineering strategy coming out of DoD talks about digital transformations, helping to address these challenges with complexity, uncertainty, rapid change. McKinsey's been talking about how this sort of digital transformation is going to help with holistic systematic analysis, right? And then MITRE said just recently published report on how DoD really needs to use better use of its existing resources to identify, protect, detect, and respond and recover from network and supply chain threats and such. And what this really boils down to is it goes back to this problem of, to do that, to really look at the system holistically, to look at how we protect that full supply chain, starts really at level zero, understanding what goes on at this level down here, and how that can then be used to measure and monitor and make sense of what's happening across those enterprises. So let's look at this, right? And so the thing that we've kind of from my time at NIST and now to where I am at the University of Maryland with ARLIS, we've been really pushing this mantra of moving from domains to viewpoints. That is, it's not a design problem, it's not a manufacturing problem, but that there's a viewpoint problem. And that is, when you look horizontally across a life cycle, really what's happening there is there's a product that's flowing from left to right. You're going from design to manufacturing to sustainment, and that really falls into a viewpoint, right? So what we've been arguing is, instead of saying this is a design problem or a manufacturing problem, let's say it's a product problem. There's a product viewpoint, and that design, manufacturing, and sustainment all have a role to play in understanding what's going on with that product. And we can start then looking at the socio-technical challenges. That is, what are at the intersection of people, technology, and policy, what are the concerns, what are the functions and the opportunities there for the design role and for the manufacturing role, right? And you can start asking a question of, how is work performed in each one of those phases of the life cycle, all around looking at the product. Same goes for the lower levels of ISA 95, right? Instead of those being just process sensing monitoring, right? Look at that as capability. That's a capability viewpoint, right? We know that there's decentralization, there's this mass sort of customization, changing demand sort of ideas around capability. We realize that OEMs don't really make things anymore. They're more integrators, and we've distributed the capabilities across supply chains. The question then is not about what process being used, but how do we look at those capabilities? And again, what capabilities design have, and how does the capabilities that design have impact or affect the capabilities of manufacturing and sustainment and so on. Same goes for operations and logistics, right? You're starting to see a theme here that it's, let's break these silos down and say, okay, what are the viewpoints, right? And in each one of those silos, how do you focus on those viewpoints? What's each function and role have to play in those viewpoints? And this gets to, since then, you can start looking at how we integrate the enterprise, right? What are those interfaces between product and capability? Really what it is the interfaces through operations and logistics, right? I'm going to have some technique to go from that horizontal vertigration or horizontal integration, and I'm going to use operations and logistics and other sorts of mechanisms to do the vertical integration to get down to the capability that has to do something for that product, right? This is where enterprise integration comes in. What is that common language that we can start using across the entire enterprise to be able to start answering questions? Because when I want to ask a question, how well is the product, for example, a car, plane, or machine performing to specification? It's not just a design problem. It's not just a manufacturing problem, because when we look at why something breaks, and I ran into this all the time in the aerospace industry, something's not performing well in operations. You may have odor in the cabin, you may have a performance problem in an engine that's hanging off the wing. More often than not, it's not the operations viewpoint or the operation domain that the problem started in, right? The root cause. It could have been a manufacturing defect. It could be a design defect. And so you got to understand, right, who can help answer these questions, who has what information to be able to answer those questions. Same thing when you look at operation logistics, right? Where can I sacrifice machines today to ensure traceability or availability of parts I must deliver tomorrow? Well, that's not just a manufacturing enterprise MES question, right? Because you have to understand, okay, what are the capabilities that I need to produce the parts that are coming in? So I have to interface back to design and understand the designs that I'm going to have to produce, right? I have to understand customer demand. So that is the delivery, the sales side of it. That all has to feed into then the operational questions I ask of, where can I take a machine offline offline because maybe I have to do some preventative maintenance on it, and I'm going to lose that availability of that capability today. But I know I've got these other parts coming. So how do I make that decision of when and where to pull that machine offline? Right. Same thing for capability, right? What capabilities are available to produce the parts I have, or how are those capabilities performing to specification, which is an interesting question when you look at that last one to the first one, right? That capability, depending on your viewpoint, could become a product question. If I'm a machine tool operator, my product, as a stakeholder, my product is the machine tool. So the machine tool operator could go back to the machine tool manufacturer and say, how well is your machine tool, AKA product, or in this case, a capability, performing to specification? You have these linkages between these questions, and hopefully you're starting to see where this interface sort of happening, right? And so are my processes performing the correct actions and so on, right, to the needed time? Moving into this, right, it's all about how do I connect information? How do I move this into having dynamic information models? How do I query the network, right? And it gets to this idea of integrated logistics. So where I want to wrap up here, because I'm running out of time, is that digital twin gets thrown around everywhere. You have to ask, what are the key components of digital twin? And I'm not going to go through this slide in great detail because I'll make the slides available, but I highly recommend you read this paper about looking at system architecture designs. It's about manual versus automated data flow. Just having a model and having a physical object doesn't mean you have a digital twin, right? And what this really boils down to is digital twin requires you understanding conceptual interoperability, enterprise connectivity, linked data, trust and traceability, autonomous knowledge generation, right? That's how you get to this idea of distributed, secure digital twins. The references are here. I ran through this really fast because I wanted to kind of just hit home in terms of the sense that we throw digital twin out for saying, oh, I have a model, I have a digital twin. Got to ask the question, do you really, when you look at that? Because digital twins can't exist without a digital thread, connecting that information together. Manufacturing operations need those tools for measuring that distributed and federated capability and capacities across those supply chains. And we've done some studies when I was at NIST that showed that manufacturing as a service will help SMEs save about $11 billion a year, right? That's with a B, just in doing better sensing and monitoring. So with that, again, ran through this really quick to kind of just whet the appetites for the question and answer. Hopefully the slides are made available, but if you want, take a screenshot because these are the references for slide 14. And I'll turn it back over to, I think James is next.
Thank you, Thomas. We'll move on to the next presentation by James.
Okay, let me share my screen first. Are you able to see my screen? In the play mode. Can you see it?
Yes, we can.
Okay, great. Hello, everyone. Thanks for the invitation from Rahul, and also thanks for the first two panelists' great presentations. I want to brag a little bit. Both of them have strong tie with the Virginia Tech. Thomas got his PhD, and Laine got his the BS. Okay, so if you guys are missing Blacksburg campus, you can look at my background. That's the aerial view of geofield. Okay, so let me know if you guys have the plan to visit the VT in the future. I will be the host. Today, you can see the title of my presentation is Sensing and Data Analytics for Smart Additive Manufacturing. So it's really focused on the additive manufacturing. And basically, first of all, I want to introduce the framework. Manufacturing it's about a material, right? Material, transfer material from one form to another in order from quality aspects. Then we need to have different manufacturing processes. Right nowadays, additive manufacturing becomes very popular. From quality aspect, okay, we need to see the process to capture the anomalies, right? So we need different type of sensors. So nowadays, with rapid development sensing technologies, and we can have a huge amount of data easily ready, right? Then what should we do, right? I'm in the industrial systems engineering department. So one of the strengths of my department in general is data analytics, right? We have the people doing quality reliability and operation research, optimization, etc. And then doesn't matter, everything in the analytics is about decision making. And it doesn't matter how good of the decisions at the end, we need actions. Okay, we need to change the process, improve the process, right? We need end effector to close the loop, then we need to control, right? So this is kind of framework, and we are following. I will use this one to think about what is my interest and how to identify the collaborators for the large scale projects. This is kind of CPS, cyber physics system type of framework. By myself, I'm not able to do so many things, right? So at Virginia Tech, we have a great atmosphere of the cross the discipline collaborations. Okay, this is the very nicely here. Okay, so and then focus on different, you see that highlights. I'm going to introduce several applications. First one is focus on the sensing part. So this is the structured light 3D scanning. And this is quite a mature techniques, but the current product off the shelf, they are not able to have sufficient the space resolution to really to capture high resolution of the data, particularly useful for the AM. So this is what we developed, and we use some tricks to significantly improve the spatial resolution of off-the-shelf technology, usually like 30, 40, 50 micron to like 3 or 4 micron. And this digital image correlation, similarly, we significantly improved the spatial resolution to the below 10 micron. Okay. And there's some also similarly for this thermal imaging has been widely used by many researchers. We see a lot of papers published in this area by using thermal images. So we significantly improve the spatial resolution, okay, below 10 microns, 3 or 4 microns. And this is just one example to show, and this is not, looks like image, actually this is 3D point cloud data. So we can achieve a 3 or 4 spatial resolution, and then we can see with this such high spatial resolution of scanning, we are able to see even the melt pool geometry very clearly. We can quantify not only surface finishing, but also the morphology, this geometrical information for the melt pool even. And there's some other example you can see before and after, and our improvement, the high resolution of the point cloud data can show many of the hidden features previously we cannot see it clearly from us. So we do have lots of sensors, but how to incorporate different sensors together? Okay, so the commercialized machine, we can hardly change anything. We develop a like very cost-effective platform by ourselves. And then we can easily put different sensors in, like all the previous one which I just introduced, including the 3D scanner and IR, thermal, and even DIC. And then this is for the metal, for the polymer machine, we installed the highest resolution digital microscopes. We can continuously capture the surface which is being printed. Okay, and then the second example is we went to the Oregon National Lab, so to utilize their synchrotron facility, and basically to capture, because their facility can provide such high spatial and also temporal images for the X-ray data. Okay. And you can see the 70 Hertz capture rate and 2 millimeters of spatial resolution. And also, this is very unique and attract many researchers from all over the world to go there to perform the research. I think the Oak Ridge, they have the similar facilities. And one uniqueness, what we did is we not only utilize their X-ray, but also put the thermal data, thermal camera in. So we have the thermal camera by ourselves, which is high, spatial, this is middle one is ours. It's high spatial, but low the temporal. And there is a very advanced one from the Oregon National Lab. Its opposite is the high temporal and low spatial. So basically what we did is how to combine these two complementary the video stream together, right? And so we applied one technique called the tensor decomposition. By using temporal decomposition, we can combine two streams which have complementary features in spatial, temporal, and combine them together. So the resulting video stream has both relatively high spatial and high temporal. Okay, this is why one applications the data science can directly contribute. And this is some verification we did in the lab to verify this method, to combine two video streams together. And next one is for high dimension data, also called modeling, is try to capture either spatial or temporal correlation. If the data totally random, no modeling can be useful, right? So for example, this is in 3D case, actually we can in general consider it's a general high dimensional case. Each point, okay, is one image, okay? And then our task is to identify the inherent data distribution. I still go back to 3D, right? This is in 3D space. If we are able to unfold this structure to identify really this is in an S shape, then actually it's possible to make it as in 2D instead of 3D, right? By using the similar approach, we can significantly reduce dimension from like a million to just a 10, right? Million, the dimension of 1 million is very typical for image data. And then by using this approach, it's called manifold learning. Actually, the PCA or long linear PCA they're also along this line. So basically, we can use this kind of approach to analyze the image data and to significantly reduce the dimension of image. And then we can use some classical either classification methods or control chart method to do the anomaly detection. This is another example I want to share how deep learning can contribute in material science. This is actually X-ray data we captured from the Argonne National Lab. And this is a keyhole, this is a melting process, this is a keyhole. Actually, what we are really interested in, another boundary is in between liquid and solid. Liquid solid boundary is so unclear in these images. And what you see, this boundary actually is between gas and the liquid. This is the keyhole. And actually it's around here, that's a boundary of liquid solid, but is, as I mentioned just now, so unclear. So we developed a machine learning method. It's called attention-aware based image classification, which can successfully detect the boundary. You see the boundary of the liquid solid and continuously predict the boundary. This is boundary. Once we have this boundary identified, we can estimate the velocity of the boundary. This velocity is directly related to the microstructure of the material being printed, which is very helpful for material science. So this is one part of the ONR MURI projects. We are working with several material scientists from the UTK and some other universities. So we can see the power of the data science, which is quite helpful, beneficial to the material science area. It's another example to identify the foreground background. So this is not this is the a video, and we have a very noisy video. We developed an algorithm to decompose this video into the static background and the dynamic foreground, and then some random noise. This is not engineering application, just want to demonstrate how it works. Then we apply this method to the X-ray video. And this original video, you see it's quite noisy. And then we can decompose into the static background. You see nothing changed, right? Static. And the dynamic moving background, you see the mail pool is moving. And the most noisy part already removed. And also this the residuals. So with this decomposition, we can capture the liquid solid boundary more accurate and more helpful to the material science type of the analysis. Okay, the last application is in the for the 3D scan data. This is in collaboration with Oak Ridge National Lab. They scanned this NIST standard parts using 3 different type of the methods. And then they did not tell us what method, what platform material are using, just labels the data set 1, 2, 3, ask us to perform analysis to see if our analysis is consistent with their understanding and observation. we applied one method called graph theory method to convert either the one image data or the point cloud data into the graph. Then the variability of the surface can be converted into the connectivity of this graph. Then we can utilize some very nice properties in graph theory, which have been sitting there for 20, 30 years for the surface, the quality verification. So we showcase our results and to show and we share with our collaborators at Oak Ridge National Lab, which is very consistent with their understanding, and we publish it in the Journal of Manufacturing Science and Engineering. Okay, again, as summary, I use this framework again. So this is really a smart everything, smart manufacturing. Doesn't matter it's traditional machining or nowadays 3D printing is truly interdisciplinary. So we need expertise from different areas. So, we need to identify what is our core competence and what is your most important angle to start with. For me, is really focused on sensing and analytics, and I do need collaborations with people from material science, with ME department, with even from CE or ECE or CS departments. Okay, this is my last slide. Thank you, guys.
Thank you very much, James. So with that, we conclude the presentations from the panelists, and we will take questions from the attendees. We have already some questions that I will direct to the panelists that we have here. So there is one question from now Malay. It's probably geared towards Thomas. How do we assess the performance of subparts of a product which are bought from suppliers? So how do you basically address that issue, because you are not manufacturing and the parts are being supplied by supply chain components? How do you assess their performance?
So I think this is a great question, and actually I think also ties in with Ryan's questions, because what it boils down to is that we have to understand that there's several business decisions that have to be done around manufacturing, and when we start looking at how data is being shared. And one of the things we need to do is understand that to measure or assess that performance of those subparts that are being purchased from a supplier, you may need information or data from those machines or from those processes that happen in someone else's factory. And what we don't have right now is good trust in the sense of how we protect that information, what sort of intellectual property leakage happens in terms of that information being shared. So we're seeing suppliers refusing to provide access to or give data to their customers on those parts because they think that gives away their special sauce. Now, those who've worked with MT Connect and understand how machine tool controllers work, I can tell you that you would need a lot of data to be able to reverse engineer the part off the machine tool, because the frequencies at which we're capturing this data is not high enough bit rates to be able to get enough information about the part to be able to reverse engineer it. However, just getting 1 or 2 hertz worth of data off of a machine tool is enough to provide you some insight in terms of the quality of that part or the quality of the process. So I think these are the things that we need to work through in terms of helping manufacturers become comfortable with and trust and have traceability in the process, which is why, I quickly on that last slide, showed that trust and traceability is a key piece of the digital twin. And tying into Ryan's question, it goes to, because of trust, right, that there's also the feedback mechanism, and that is that manufacturers want to automate things, but they also want to have control over that automation, because we have to keep in mind that manufacturing has very thin margins in terms of profitability. And when a machine tool breaks or goes offline or something happens in the process, right, that company's not making money, right? And so providing automated feedback or providing the customer with data to then come back and say, thou shall do, right, is very disruptive to that process. So I think this is where socio-technical sort of analyses come into play, because this is not a technology problem. This is a human and a policy problem in terms of how we can enable assessing performance or the quality of parts in a distributed environment, and how you enable those digital twins to really work.
I can comment on this also. You know, you're exactly right, and we're really just scratching the surface. If we look at the automotive industry, this has gone completely over to a supplier-driven system. The OEMs now are doing relatively snapping big modules together, and so there are different types of suppliers. There's suppliers of bolts, right, that are pretty easy to track down, and then there are suppliers of things like turbochargers, right, where you've got some real knowledge, you know, built into the design. We communicate with those suppliers through these weird things called specifications, which are very clunky, and things like tolerances, and they just don't make a whole lot of sense when you're talking about functionality. And so being able to translate the manufacturing variation into functionality variation, that's an area where a lot of work can happen. And that's an area where machine learning, and an area where this data sharing and all the stuff that Thomas is doing is really, really important.
Thank you, Laine and Thomas, for answering that question. I have another question from Chandan, and this is to Dr. Kong, and it is about, can we measure the characteristics of the melt pool in 3-dimensional in real time? If yes, what are the attributes and how can we capture them?
Right, this is great questions. And even now in the organization lab, I think the X-ray, as I showed, it's just 2D. It is still not 3D yet. And however, based on this 2D, we can have some assumptions. For example, the conic shape, etc. We can measure the depth of the melt pool, even the depth of the keyhole or width of the melt pool keyhole. That's very much useful for the microstructure prediction and the mechanical property prediction. But this question brings a very interesting, the issue is sensing techniques for additive manufacturing. So I think that now some researchers are investigating the so-called in-situ XCT, and which make the kind of real-time 3-dimensional scanning, and that's quite impressive, but I believe it will be quite costly for that one. Right.
Thank you very much, Dr. Kong. There is one more question related to the additive manufacturing one, which is, you said that it is very difficult to identify the liquid-solid boundary in the problem. So how do you collect the ground truth data so that you train your deep learning models on that?
Right. Again, this is an excellent question. So whenever we do this analysis, ground truth, we try to capture that one first. For this one, we really, because it's a real world application, we really do not have that golden ground truth. And what we identified is we have the video, and our students identify those videos frame by frame using some of the image processing techniques, and so to enhance the boundary. So eventually we are able to detect the boundary, which previously, if you directly observe the videos, almost invisible, right? And through this kind of frame by frame, the boundary enhancing, we are able to do that. It's just too tedious. Okay, it's just it's not good ways. Each time we have like maybe thousands, even more of the video frames to handle, right? So our what we showcase here is really we have very fast and effective methods. Use deep learning. Just use a couple of the frames instead of the entire frames of the image to do the analysis. Then we compared with our deep learning result, which is based on just a couple of frames. To compare with that kind of ground truth, we build manually frame by frame. Right. That's kind of the way we are using.
Thank you, Dr. Khan. I have one question for Laine. I really find his, the diagram on Industry 5.0 very, very interesting and forward-looking research direction. So Laine, in terms of like human technology aspect and going how that is going to affect manufacturing in the future, can you, provide some of our attendees with your vision where machine learning and data science is going to be useful in next 5 to 10 years, especially in terms of human technology, data collection and uses in the assembly or manufacturing plants?
Yep, this relates nicely to the earlier question about human comfort, and I take comfort very seriously in terms of human perceptions. Different people like to perceive things different ways, and different people perceive things different ways, not of their own volition. That we all have a different way of looking at the world. And associated comfort levels that go along with that. There's a ton of stuff that I had no idea existed from the psychological domain about how people feel stress, how stress changes over time, and how to affect stress. It's almost like this self-help books, and the things that are related on how to feel better and how to live a better life. Those have some real sort of scientific bases to them. That can be applied in this domain as people start to interact with with equipment, and we get past this idea that robots are stealing my job, and how I'm going to have personal stress, related to trying something new. And this resistance to change in the first place, and what we call the modern Luddite, or you want to damage the equipment to get it out of the way so you can go back to doing things the old way. I think that data is going to give a sense of cushion to the worker. And now, as we start, I mentioned artificial intelligence, but I didn't get too deep into this. As we start to look at artificial intelligence, and we start to see the emergence of systems which can make decisions, can do some of this complex scheduling stuff that computers could never do before. Now we're starting to feel threatened at the frontline manager level, and at these back office kind of jobs. It's not just the person on the floor who's trying to put the screws into things. It's people like material planners. Their job may be going away, and using data and information and communication between the automated system and the human in both directions can help sort of soften that and take away some of the mystery and take away some of the fear. That's a nice soft answer, right? It's not like hard data stuff, but I think that this is a real important evolution in manufacturing that we need to pay attention to.
Thank you, Laine.
4.0, 5.0. Nice. Thomas,
there is one more question you want to ask all the panelists, because most of our audience are typically students or people who are interested in data science and machine learning, which is, according to you, what are the attributes of a good data scientist, machine learning, and what emerging skills do you recommend for students or aspirants who wants to enter the data science, machine learning, and AI space?
Ooh, I'll go first. So I think one of the things that drew me, I was not looking to leave the federal government when I went to Maryland. I was actually, I had a fun program that I was able to develop and was leading. But one of the things that drew me to ARLIS is that we focus on the human domain aspects of hard problems, right? And that is, how does the human fit into with all these things? And we're really taking these socio-technical approaches. And this goes to actually Ryan's second question that I just answered in the panel chat there. But it's data science isn't all about the data, and it's not all about the tech. You have to understand the people side of this, right? Where do the people fit into that? How, who's performing the work? How are they performing the work? How's that work organized? Understanding that psychosocial piece as well as the physical piece, and all those interactions between the person with the machine, and then the person and machine working together, interacting with its external environment. So that's I think the key piece is that data science isn't just about data. It's not just about putting fingers on keyboards, ingesting a bunch of information in ones and zeros, watching the electrons, spit across gaps. It's about really understanding how do we augment and enrich the human who's doing a function to make better decisions. Because as I think it was Laine's slide about Lee's work in terms of humans being able to adapt, it's very true. Humans are really good at making decisions when presented with you high quality information, and in that. So I think you have to understand, what's the purpose of the data science? Is it simply just to do data science for data science, or are you actually trying to achieve some outcome? Who's the stakeholder of that, and really approach it from that perspective? If you did that, you will be far ahead of a lot of other people.
I can also share some of my thoughts. I think I assume all the audience are the engineering students, right? So I think perhaps we first think about what is our core skills, core competence, right? And how to use data science to help us enhance our skills and our capability, right? For example, in material science, there's a huge amount of different microstructure, EBSB, TEM, naturally they are doing a lot of signal processing. In Dr. Lei's lab, there's a lot of the wearable sensors, right, that need a real-time computing capability. Right? So basically, data science is almost everywhere, but don't try to compete. Don't imagine, don't consider you as a consultant. We are still an engineer, right? So identify your like research area, your application area, then try to learn the so-called data science to help to your further progress in that regard. Right?
Yeah, my only advice in that, it's twofold, is data comes from sources. And if you're looking at, for instance, manufacturing, go out and see the source so you can understand sort of where it's coming from and what the data represent in the physical world. That's one side. The other side is learn some coding. So that's going to be sort of essential now that we're all engineers have to be a little bit of computer scientist now, or at least able to handle the data, format it, analyze it, and there are great tools for doing that. You don't have to invent that. So I think the days of Excel are going to be sort of floating away. We're going to start getting into some more sophisticated tools.
Thank you, Laine, Tom, and Dr. Khan. With that, I would like to conclude. But before I conclude, I would really like to thank all the panelists for spending their valuable time with us and this community, and helping us build up this community where we are trying to do an outreach activity for bringing everyone who is interested in the applications of data science, machine learning, AI. With that, we will conclude this webinar, and we will come back next Thursday again at 11 a.m. EST, where the next webinar is focused on industrial applications of data science, machine learning, AI. Thank you, and have a great day.